You can get really frustrated trying to learn if you're using a monkey see, monkey do approach to reverse osmosis. This video will teach you the basics of this technology and increase your comfort level as you work in this field. RO is shorthand for reverse osmosis. The idea of RO was developed from the discovery of osmosis by Henri du Chauchet around 1826. Du Chauchet was a French nobleman hiding in his family chateau during the French Revolution. He passed the time by looking at plant cells with his microscope. He saw that the cell was like a bag of water that contained a collection of small bits and pieces. Water passed through the cell's membrane, the loose bag that surrounds the cell. But the membrane wasn't just a wall with holes in it. In some fashion, salts were blocked from passing through. Henri and later others observed that water flowing into or out of the cell depended on the salt concentration across the cell wall. If there was more salt in the cell, water flowed in. If there was less salt in the cell, water flowed out. And if the salt inside was the same concentration as outside, the flow of water in matched the flow of water out. As you would expect, as water flowed into the cell, pressure would increase, sometimes even past the burst point. When the water flowed out, the cell would lose pressure and collapse. Henri that it did not make any difference what salt was involved. The same flow pattern was seen if the salt was table salt or calcium chloride or whatever. Henri's work revealed the following. Membranes are more than bags. They let water pass but hold back salts. More salt in the cell, more water flows in. As water flowed, the cell pressure would change. Different salt, same pattern of flow. It took another 100 years before chemistry and physics caught up to Henri's observations. After Henri's time, we began to understand that everything was made up of atoms and molecules, and that these incredibly small particles were always in motion. Think of a soup pot on the boil. When we add a membrane to this soup, only the water can move wherever it wants. Each water molecule has a 50-50 chance of being on the left or the right side of the membrane. The salts are stuck on whichever side they started on. In our picture, there are more waters on the left, so more waters are available to bounce to the right side. What we see through the microscope is a flow of water left to right. If we want to see osmosis with the naked eye, we can set up a lab experiment with a U-shaped tube divided into two sides with a membrane. Water has flowed left to right, lowering the level on the left and raising it on the right. Also in the figure, the membrane is called a semi-permeable membrane. A membrane that allows water to pass but blocks the passage of salts, sugars, or other types of material that dissolve in water. Only RO or other type membranes are semi-permeable. Will the water continue to flow left to right until the left side is empty? No. Opposing the flow of water from left to right is the flow from right to left. This flow is driven by the pressure difference across the membrane created by the difference in the height of the water. At some point, the flow due to the salt concentration difference is equaled by the flow due to the pressure difference. Osmotic pressure is the pressure difference across the membrane when the flow left to right is equal by the flow right to left. One of the ways to measure osmotic pressure is to put a piston on the right-hand side and measure the pressure required to keep the two water columns' heights equal. If you were to do this experiment, you would find that pressures higher than the osmotic pressure would force water to flow from right to left, i.e. the salty side to the less salty side. When you reverse the normal flow, instead of osmosis, you are now doing reverse osmosis. And instead of pure water flowing into salty water, you are producing pure water from salty water. Reverse osmosis is the production of pure water from salty water by applying pressure to force water through a semi-permeable membrane, leaving the salts behind. Once discovered, reverse osmosis was studied and became well known in the scientific community. For many years, substantial barriers kept RO from entering mainstream water treatment. To be of practical use, a membrane had to be developed that was semi-permeable and required as little pressure as possible to force water through. After many years of federal funding through the Bureau of Reclamation, a practical RO membrane emerged from the labs. The membrane that was developed, the thin film composite membrane, has become the workhorse of membrane water treatment. The stuff we've covered so far, you should have a good physical understanding of these terms: osmosis, osmotic pressure, reverse osmosis or RO, semi-permeable membrane, thin film composite or TFC. In our next chapter, we will move from what reverse osmosis is to how to make it work in the real world. See you there.